with a presentation of Apoorva Patel on understanding the Born role in weak quantum measurement. Please.
So I thank the organizers for giving me the opportunity to describe my work on weak quantum measurements. The purpose of this exercise is to understand what happens when you make the coupling between the system and the apparatus small. And so the standard explanation of the result of measurement being described by a step function will be rounded off in some manner. And the purpose is to understand what is that kind of process going to teach us. And experimentally it can be tested, and we'll see what are the implications. So just to set up the framework, the axiomatic description in standard quantum mechanical textbooks has two components. One is a unitary evolution described by Schrodinger evolution. It's continuous, reversible, and deterministic. And pure states evolve to pure state. The second component is a projective measurement, typically known as von Neumann postulate, which is described in terms of a set of projection operators. And it is a discontinuous step. It's irreversible. The choice of which projection operator will show up in which particular instance is probabilistic, but it still evolves pure states to pure state. And the description is such that if you repeat the process, the result does not change, because the square of the projection operator gives you projection again. What is missing in this description is the prescription that if I make a particular experimental run, which projection will occur. What you have is a kind of average or ensemble description, but it does not give any idea about individual steps. And this is generically the centerpiece of the measurement problem. You do not have any idea about individual experimental determination, and I'm going to call those individual parts as some kind of trajectories, which when combined together give us certain results. In the description of this type, Born rule and the state collapse are generally mentioned together, but these two parts are actually separate, and you can construct a formalism where they are independent and that teaches us something, and that is the purpose of my talk. Of course, the average procedure or the ensemble result is well verified. It takes the density matrix to this particular combination averaged over all the projection operators. But to check that, you have to perform the experimental run many times, starting with the same initial state. Okay. So what does weak measurement do? You extract the information from the observable at a very slow rate, which is essentially weak coupling. And what does it do? It stretches out the time scale which is associated with collapse of the system to a particular eigenstate of the measurement operator. And this process can be given a quantitative description, which I'm going to describe. Of course, the measurement can be described in many different ways. I'm just going to take a simplistic interpretation that for whatever reason, the measurement interaction does not produce a superposition of the pointer states which is visible on the apparatus. So let's see what comes out of it. This kind of description also poses many other questions which are beyond the quantum axioms which I just listed. Can this prescription work for all measurements? What is the local evolution rule of the dynamics? What happens if you leave the measurement incomplete because the coupling is small and I can turn it off in the middle? What happens when there are multiple measurements going on at the same time because there is now a time scale for the measurement process, etc., etc. And they all have to be answered. In practice, you can use this kind of understanding to improve quantum control and feedback. And that is because we now have an idea about what is happening in a particular experimental run and not just the ensemble average. So of course, we have to go beyond the projective axioms to a different kind of stochastic dynamics. So there are two kinds of descriptions which are available. I am going to go with the continuous trajectory formulation, which is continuous, stochastic, and tractable. But there are also many works which describe the process of a quantum jump, which is discontinuous. It can also be tackled in a similar framework, but I'm not going into that particular detail. So how does this process go on? That you can construct these quantum trajectories. It requires two components. One of them is a deterministic evolution and another is a random noise. But these two things are somehow tied together because we demand that this combination does not violate the laws which you have already understood. And they are just the simple statements that the measurement outcome must be repeatable, which means that the eigenstate of the measurement operator have to be a fixed point of the evolution. If you have reached the eigenstate, you cannot go away anywhere else. So whatever noise and the deterministic part of the evolution, they have to stop. And this makes the dynamics nonlinear and non-unitary. Once you reach the fixed point, you cannot figure out where you came to the fixed point from. The second part is we demand consistency with special relativity. So when we have extra time scale, it should not destroy probabilities of measurements in multipartite measure situations. And that means that I have to remove any conflict between the Born rule and special relativity. And one way to do it, and that works out well, that during the measurement process, Born rule is a constant of evolution, even though it is stretched out in time. Of course, this is a probabilistic statement to show that it's a constant of motion. You have to average the overall distribution of the noise. And this kind of description was written down by Nicolas Guisson many years back. And I'm going to give the ingredients for it and emphasize what we can learn from this description. So what is a part of this description? I'm giving the answer first, that you need to add evolution towards the eigenstate and an unbiased white noise to reproduce the Born rule. But these two effects are not independent. They are actually occur with a fixed ratio, and that connection is reminiscent of the fluctuation dissipation theorem, the attraction towards the measurement eigenstate is a dissipative part, the noise is the fluctuating part, and they are tightly constrained, and which means that they have a common origin somewhere or the other, just like they appear together in statistical mechanics, where the common origin is molecular scattering for both these processes. The second thing is this connection between the deterministic and stochastic part means that they have a common origin, and so whatever is driving you towards the eigenstate is also giving you the probabilistic description, and the rest of the environment doesn't appear connected to the process except through the apparatus which is performing the measurement. So somehow surprising part, but we can forget about the rest of the environment while describing this evolution. And pictorially it is kind of easy to describe. This is for situation for a qubit. We are trying to understand measurement as some effective process of a more fundamental theory. You start somewhere and then you zigzag towards one eigenstate or the other eigenstate, and this zigzagging process can be measured in experiment. It can be quantified in theory, and if you have good understanding of it, then you can maybe predict something more. Okay, so now let me start with the mathematical part. First part is just understanding driving from a particular state to the eigenstate. And this is a kind of average description, since both the initial and final state are pure states. It can be just modeled as a geodesic evolution. And this is a general equation for the geodesic evolution of a density matrix going towards some projected eigenstate. You can derive it in many different ways, but just can understand it in a very simple terms, and that is described by this operator. This operator has actually connections to many different processes. I will come to that. And it's a differential equation. It's a continuous in time. What are easy things to notice about this result? This is nonlinear evolution, but it preserves pure states. So rho square is equal to rho during this evolution. The projective eigenstate is a fixed point of the evolution as you require. If you have bipartite stacking where rho is made up of two components, the decomposition of the projection operator into the two state means that I can sum over all the unobserved degrees of freedom, say the projection on I2, and get the same equation, because the equation is linear in Pi. It is not linear in rho, but it is linear in Pi. So all the unobserved degrees of freedom can be summed, and it does not modify the equation at all. And the interesting feature is that this equation can be written in terms of the well-known Lindblad operator, as the Lindblad operator acting on the projection state with a negative sign. So this is very suggestive that it is actually the state which acts on the apparatus, and what happens to the state is a back action, which is denoted by this minus sign. And this is a action-reaction relation, which is understanding and are important to understand to get some idea about the dynamics involved. So now I put together not just one eigenstate, but many eigenstates. I took the same equation and put in some weight in front of it. The equations still go through, rho square equal to rho is preserved, but now every pi is a fixed point. And wi are some weight which I have to decide to get the Born rule correct. And they depend on whatever the observed degrees of freedom are. All the other extra degrees of freedom, the pi of the environment can be summed up and disappear from this result at all. And the point is that the sum is here done over the degrees of freedom of the density matrix. It is not the wave function which appears here. There are other characteristics which also shows what is the role of the environment, that if you take this equation and calculate the evolution of the off-diagonal density matrix of rho, it is completely determined in terms of the diagonal density matrix. And so the off-diagonal element are not independent of what is happening to the diagonal processes. And so this measurement dynamics is actually completely decoupled from the decoherence process. The environment can do other things, but I can ignore that as far as this measurement dynamics is concerned. And there are only the n-1 degrees of freedom compared to the total density matrix, just the diagonal projections which are independent degrees of freedom. Okay, sir?
Geodesic with respect to what distance?
You can?
When you tell geodesic in the title,
there are many geodesics from the initial state to all the individual projections eigenstates. From the starting state, each eigenstate is a fixed point. So this is a sum over many different geodesics. It's a simultaneously diverging process. You still don't know where you will end up. But
okay. Then you construct this equation with hypothesis that all the pointers.
They're all geodesics still together. I have not put in the part which will produce the collapse. The collapse will come, which will decide which geodesic will be observed in a particular evolution, but I'm trying to separate it as much as I can.
What is the metric behind the geodesics? Because for geodesics, you are on a Riemannian manifold.
Yes.
And you need some metric structure.
Standard Hilbert Hilbert space metric. It's a unitary sphere.
Frobenius metric. It is the Frobenius metric.
It's a unitary sphere. You take the unitary metric on the sphere just as a distance. Nothing. It's a vector space. You define coordinates and take the metric. There is no extra label needed for that. In particular, if you take a qubit, it is just the great circle connecting the 2 points, nothing more than that. So now comes the question of figuring out what weights will produce the correct result. And for that, you can focus on the diagonal elements one by one and write down the corresponding equation. It is not too complicated. It actually tells you that the weights which are bigger than the average, they grow, and weights which are smaller than the average, they decay. But this is not what we want. So if you take the weights to be just the instantaneous Born rule corresponding to whatever density matrix has that particular point, it will just converge to the closest fixed point, and that result is not in agreement with experiment. So we cannot choose such a weight. And what allows you to reproduce the Born rule is to add some fluctuation in this weight, that you just do not go directly to the nearest fixed point. You wander around in the state space and explore other possibilities, and such things are well known from statistical physics. You just add some noise to the geodesic dynamics, so you explore various possibilities. Of course, you have to keep in mind that you may choose various ways, but the normalization constraint will remain. This kind of adding of noise is certainly not universal. It depends on the particular apparatus or the operator that you are trying to measure, and we'll see a particular solution which is consistent with all that. And that solution is explicitly worked out by considering the single qubit situation, because there is an exact analytical result. And this comes from the fact that there is essentially only 1 degree of freedom left because of all the constraints. The total probability is 1. The total weight also has to be 1. So you write W0 and W1, but the only non-trivial component is W0 minus W1. And the equation which I wrote can exactly be solved for the off-diagonal elements. As I mentioned, they are not independent of the diagonal elements. And this is an analytical expression for that. And now you can ask, how are you going to make it consistent with the Bond rule? So the Bond rule is obtained by adding this noise on top of what is the instantaneous diagonal elements. If I don't put this noise, I will just go to the nearest fixed point. The W0 and W1 are just the instantaneous component of the density matrix. But this is a noise which is added as a Gaussian unbiased white noise, defined by zero mean and a delta function correlation for the variance. So this then becomes a stochastic differential process on this interval 0 to 1, because these weights are bounded in this particular interval. The fixed points remain, rho 0 is equal to 0 and 1. They act like a perfectly absorbing boundaries, and the noise will give the zigzag evolution between these two boundary points, and that is just a 1 degree of freedom description which can be studied analytically, and it can be also implemented experimentally. So this is a kind of picture which comes out to make a simulation in presence of a noise. This is the analytical part. Every realization of the noise will give you some description, and there are basically two components going towards the two boundaries. They don't go toward the boundary in a monotonic way. So it's a highly irregular process, but it is still continuous process. And this particular illustration was constructed by starting at the symmetric state in the middle, rho 0, 0 equal to 0.5. So let me now give various properties of this particular noise, and they can be understood by varying the magnitude of this particular noise and see what happens. If there is no noise, I will just go to the closest fixed point of the evolution, and if there is only noise, then probability of going to the either part is equal, and the true answer lies somewhere in the middle. And what is that answer? You can understand that very easily by converting that stochastic equation, which I wrote down in the Stretnovich form, to the Ito form, which describes only forward evolution of the dynamics, and that can be done again by using the standard rules of stochastic dynamics, and the expression then now becomes of this particular form. There is some coefficient of dt and some coefficient of the noise. The noise in the Ito process is called the Wiener increment. It is just the same variable psi multiplied by dt. You can model it as a random walk if you want. It has a zero mean and a particular variance, but there is an extra term which is proportional to dt, which describes what is called a drift. And if you want to generate the Bond rule, what is necessary that you do not have this drifting term at all, and that basically determines the magnitude of the noise, that G times Si is equal to 1. It's neither this nor this, but somewhere in the middle, and then you have a pure Wiener process modeled by a random walk, and what it does is the average of rho 0, 0 over the noise becomes 0 because I eliminated this drift term and only kept the noise in the Wiener process, and that means that the Bond rule now becomes a constant of evolution. So there are two components, a drift and a diffusion. I eliminate the drift and have only the diffusion, and then the whole process still describes a stochastic dynamics, but now it is a process in which Bond rule is guaranteed at every instance of time. So even if I stop the process in the middle before reaching the fixed point, Bond rule is not violated. The evolution dynamics can be worked out by conversing the stochastic dynamics to the Fokker-Planck equation, which describes the whole distribution, and you can draw lots of pictures with that, no problem. There are basically two components which come out of the solution of the Fokker-Planck equation. One goes towards one eigenstate, the other goes towards another eigenstate. If you use the suitable variables, they can even be made to look like Gaussian. So that's easy to understand analytically, and this actually can be tested in experiment. What happens in this whole analysis is, for a qubit, there is nothing left as a independent degree of freedom except for the time integrated value of the coupling. There are no other degrees of freedom at all in the solution of this equation, and so you can choose various couplings, various kind of distributions, and see the process, and the description is consistent with all the choices. Some choices are simpler than the other, like you can make it a nice Gaussian, but you can also go to an extreme where there is only Z2 noise, which means there is only some plus epsilon and minus epsilon on either side of the mean. That is also completely okay. They all produce the same evolution as far as the Fokker-Planck distribution is concerned. So here are the pictures, again, analytical result. You start with some value of the initial state, some delta function, and you see what happens as time develops. So it broadens out at the first, and then afterward it starts to converge toward the two sides with some peaks around it, and ultimately it will become two delta functions distribution on either side. The only parameter is that integrated value of the coupling over the time, and the numbers which are written over here are actually the value of this integrated coupling. It's a dimensionless parameter, and you can put numerics explicitly inside it. For example, if the tau is bigger than 10, 99% of the probability is within about a 1% of either of the fixed points. So this is a nice analytical result, and we tested it out in an experimental setup. This was done by using the data which was provided by Vijay Raghavan's group at TIFR, and it became Parveen Kumar's thesis work is here somewhere. It was several years back, and it was a nice confirmation of the ideas. I will skip the details of all the experimental stuff, but I just show the figures which are enough to give you an idea. So the weak measurement corresponds to setting up the apparatus so that you have a Stern-Garlach kind of setup with two slits, but the two Gaussians describing the two slits overlap very tightly. So there is only slight difference between them, and then you vary the time. And this was all done with superconducting transmon qubits, and we have to include some features because the quantum states are decaying, but that doesn't create too much of a complication. And here are the results with some initial state and observed at different intervals of time. And we started somewhere in the peak in the middle, and it gradually spreads out and gives a nice fit to the observed data with chi-square, which are quite reasonable. And the only parameter was the time integrated coupling. That T is actually the clock time. And so all these things occurred within 50 microseconds or so. And G was actually fitted because the total tau is integral of G dt, and they could find a corresponding value of G by fitting all these various results. So this is one set of results. There's another set of results with a different initial state. Again, the fit is very good. But what this figure shows is the effect of the excited state decaying, which is a part of the apparatus. The green lines are the results if there is no decay, but we put in some explicit decay time, which happened to be about 45 microseconds. And then again, an excellent fit was obtained with the experimental data. And what did we learn from it? That this is another interesting result, that we could start at different values of the initial state on the Bloch sphere and see its evolution in terms of the weak measurement. These are two different instances corresponding to different strength of the weak measurement, but what we could easily see that the same relation between tau and T was obtained irrespective of the starting state. Once the value of the coupling, the weak coupling was fixed, you could describe evolution of any point on the Bloch sphere with very good accuracy, and that is something which was required to have this thing as a meaningful description. So, okay, that is all the experimental stuff. And now let me get back to what did we learn from this whole exercise. So one can write down again analytical result, separating into two parts by looking at the magnitude of the geodesic evolution and the magnitude of the noise. And both are actually functions of the coupling with the apparatus, which is this value of G. But what we observe immediately that you can actually eliminate the value of G and convert it into a fluctuation dissipation relation. There is a second moment which is related to the first moment of the evolution. And this is a important point of the dynamics. It is not a peculiarity of the what you call the quantum process, but it is the fact that this is a fully constrained unitary evolution. You cannot escape this relation between the first moment and the second moment as long as you have a detailed balance in the evolution. And the unitary dynamics actually provides you that detailed balance, and that tells you that the Born rule actually is a very special result. It is not arbitrary dynamics of a stochastic type interacting with the external system where the first and the second moment could be completely independent. And this has an implication that the environment can influence the measurement process, but only via the apparatus. Was a completely independent fluctuation coming from the environment, then this relation will not work. Another feature which is worth interesting in this analysis, you can ask what are the weights and what are the ranges available to them. In case of qubits, the weights have to add up to 1, and so only one independent degree of freedom is there. But this independent degrees of freedom turns out to be non-classical, irrespective of what weight you choose, and that means that the weights actually go outside this interval, though they add up to 1. And this is the quantum signature, which is present, and it has to be present to justify the appearance of Born rule. Without that, you cannot get that particular result. You can construct this weight many different ways. One of them is a Gaussian distribution, when the part which goes out of this bounded tail can be described by the error functions. Or actually, you can ask how tightly restricted this distribution I can make. And in that particular case, the weights which are the smallest variance is a Z2 noise. And even if you put a Z2 noise, you find that some part of it does go outside this interval 0 and 1. You can find out what is the value of that part which goes outside, but the important fact is there is a little bit of weight which goes outside the interval, and without that you cannot have the Born rule satisfied. So this is a non-classical signature, not like the Bell inequality kind of stuff where again negative weights have to be invoked to understand it, but just in the process of measurement of a single degree of freedom, there is something extra. And now comes the final question, which I have avoided so far, and the reason being that I don't have the answer for it, but we can ask now that, yes, you separated out all the dynamics of the Born rule, where is the projection? And the projection is still sitting outside. You have constructed a distribution with the right probability distribution, and the key component was this detailed balance, which provided a relation between the apparatus-dependent noise and the system-dependent Born rule. It's all completely fixed. The projection now has to be consistent with it, and you can ask what is the process which can provide this detailed balance and yet choose one of the many possibilities. And that now comes down to what is going to happen inside the apparatus, which is basically amplification. And the amplification we know has both components, a reversible one and an irreversible one, or in a different context in stochastic processes, spontaneous versus stimulated part. Simulated part is essentially taken care of by this tight relation, but there is still something extra which happens in every stochastic process, and that is the question of what is called the Heisenberg cut. At what point the dynamics of the quantum degree of freedom becomes classical in terms of what is observed as one of the possibilities on the apparatus, and that is now shifted up. It's not part of the Born rule anymore. You already have the convergence or on the eigenstate as a generic distribution well defined by various dynamical equations. And we can ask that all this separation of the Born rule, does it tell you anything more about the Heisenberg cut? What are the constraints? And there are some things which people have explored, and I will give you my interpretation of it, that the typical process of amplification in the experiment is defined in a quantum language using coherent states. And the coherent states smoothly evolve from initial small amplitude to a large amplitude, which will become classically observable. The mathematics is very clear, and the pointer states of the apparatus are essentially identified by coherent state where this parameter alpha is large in magnitude. One can write down various equations for it. What is the corresponding interaction which will amplify this alpha from a small value to a large value? Those are straightforward. And what it ends up doing is you have a macroscopic entangled state, which is just the description that the initial state can be a superposition, and the final state can be a large entanglement state. The fact that the C0 and C1 are appearing here is nothing but the verification of the Born rule, and those who have learned quantum circuits will realize that this is a control knot operation. And so you can have all kind of features, driven process, irreversibility, etc. can occur, but the irreversibility has to be put in on this as a particular boundary condition to convert this entanglement into projection. And this is the final step. And what is the interpretation? Well, my interpretation of what is called a dividing line between the system and the apparatus is the dividing line between the classical and quantum physics. You move what you call system and what you call apparatus by changing the boundary. Well, what is classical and what is quantum, which correspondingly change. Whatever you put in the system all becomes quantum, and whatever you leave it outside, which becomes classical. And so the Heisenberg cut is not any physical quantity determined by some parameters of a certain size, etc. It's the boundary essentially which we impose between the system and the apparatus, and that essentially tells you where you put the projection as an extra feature. And the final statement which follows from all those things is that if you are going to invoke any new feature like a gravity, in this dynamics, the only way any new feature can appear is through the state of the apparatus. It cannot act directly onto the system from outside, otherwise it will violate the measurement process and the Born rule itself. Yes, the apparatus can be large and something can be involved inside it, which can be part of the gravitational interaction, but extra interaction cannot influence the measurement process. So that's where I will stop. Thank you.
We have time for one short question.
Thanks very much. If I understand well, what you call fluctuation-dissipation relation is the fact that when you write the stochastic equation in Ito, the drift vanishes totally. This is a constraint that you impose in order that there is no drift when you write the stochastic equation.
Can you please repeat? I'm not able to understand.
Yeah, my accent is bad. Can you come back to the slide with the fluctuation relation, fluctuation-dissipation relation?
Equation for noise.
Yeah. Yeah, perfect. So if I understand well, what you call fluctuation-dissipation relation is the fact that when you write your stochastic equation in Ito convention, the drift vanishes totally.
Okay. I'm still not able to understand the
because of my accent.
Your accent is
yes,
different.
Okay.
I can talk a little bit later. That's okay.
I think you can discuss later after that on the blackboard and so on. I think it will be much easier. So thanks again. And we will